welcome to Challenge 2 in the medium difficulty series. This one is entitled A Circle and Two Squares. Imagine a circle and two squares, a smaller and a bigger one. For the smaller one, the circle is a circumcircle, and for the bigger one, an incircle. So it's probably easier to refer to the diagram below here. You'll notice the circle, there's a smaller square. It's off a little bit, but just imagine it's perfectly drawn within the edges of the circle, or the boundary of the circle, if you will, and the larger circle that goes around the outside and again runs sort of tangent to the circle. So you are to create a function that takes an integer, which represents the radius of the circle, and returns the difference of the areas of these two squares. So they give some examples. We will figure out how to make sense of this as part of the solution, and any notes, only use positive integer parameters. Yeah, -1 wouldn't make sense. I think they're trying to tell us that they'll only give us positive values, so that's fine. If you'd like to check and just do a quick parameter check before proceeding with your solution, feel free to do that. It's good practice. So let's look at this diagram and kind of figure out a way to do this. So I guess the first question is, how do you determine the area of a square? And we know about squares that all sides are the same length. So if we can determine one of those, we can simply square it, right? Because the area of a square or a rectangle is its length times its width. In the case of a square, the length equals the width. And so we can just say the value of one side squared, and that gives us its area. Okay, great. So in terms of the large square, we can actually determine one of these lengths right away. What it's going to be is, imagine the radius of the circle here, and if you double it or use the diameter, that matches with one of these edges of the square perfectly, right? You can see that it's the length of the diameter of the circle. So that's good. We can get that quick. We can double this input parameter and come up with a length of this side. So now on to the inner square. It's a little more difficult, but we can see again, it doesn't stretch across like the large square did, but notice if you kind of do a diagonal thing here, we see again that it is the diameter of the circle. It goes across and is equal to the diameter, just like this longer edge on the outside square. So again, we can double the input and find the length of this diagonal. Now you know this is a right angle, it's a square, and we know these two sides are equal length because it's a square. And if you remember Pythagoreans Theorem, a squared, we'll call this a, plus b squared, we'll call this side b, is equal to the hypotenuse, the length of the hypotenuse squared. So we can do some algebra there to get the side, the length of one side of this square. And then finally we can square that to get the area, and we can subtract the two areas to solve the problem. So that's the idea. I suppose I should have maybe had you pause there and think about it some, but there you go. We still have the work of coding, so you can pause the video now if you'd like to have a go at that. So we saw the diameter was pretty relevant here, so I'll say int diameter is equal to the radius times 2, right? Okay, that's helpful. And then really I like to make a plan here. So in general, we're trying to say get area of large square, get area of small square, return difference of areas. You know what I mean? So if you can imagine, if we had some magical method that did this and this, we can simply return the subtraction of whatever two values these things return. So this is a nice high-level way to describe the problem or how to go about solving it, and I think it could be a nice little roadmap for us. Now we see we have this get area, and that's going to be the same because we're dealing with squares. So I'm going to sort of factor that out into one method that we can use repeatedly. And because we're dealing, remember, with Pythagoreans Theorem to determine that one side, it's quite possible that we won't get whole integer values out. For that reason, I'm going to return a double. I'm going to be working with doubles for some of these helper methods. So let's call it get square area. It's going to take an integer value. Actually, let's have this do a double as well. We're going to keep everything precise till the end, and then we'll convert back to an integer so that we don't get a lot of drift as we're working. So double get square area, let's call it side length. And this is pretty easy, right? Return side length times side length. Okay, so now we got something to get the areas of a square. So then basically both of these concepts can use that same method. They'll be different in what they pass as a parameter. Now we know the side length from the large square very easily. Remember, we said it was simply the diameter. You can see that in this drawing here. This line corresponds directly with the diameter of the circle. So to get the area of the large square, I can say double large square area equals get square area diameter. Okay, and actually we called diameter as an integer. Let me just make this a double for now. Keep everything matching with our method here. So we got that. Now the smaller square involved a little bit more work, so I'm going to make another helper method for that purpose. And what I want it to do is sort of, I will give it a hypotenuse length, and from that I want it to extract what one of these legs would be. So I'm going to provide this value, the hypotenuse, and then this helper method will do some math to tell me what the length of these sides are, and they're the same because it's a square, so it doesn't matter. But that's the point of this helper method. It's going to simplify the process of getting the area of the small square. So let's call this something like get side length from hypotenuse and hypotenuse length, something like that. Now let's think about this, right? We said Pythagoreans Theorem, a squared plus b squared equals c squared. And you should be familiar with this. If you're not, you definitely should be, so look it up if you haven't heard of that. Now, we know that a and b are the same because it's a square, so we can rewrite this as a squared plus a squared equals c squared. And you can combine that to 2a squared equals c squared. Okay, so if you divide by 2, to each side, you can get a squared equals c squared over 2. And then finally take the square root of each side, and you're left with a is equal to square root of c squared over 2. You're basically taking the square root of this entire quantity. So, in this case, we know that c was the hypotenuse that's given to us. So I could go return math square root to square it, we'll multiply by itself, and then we can say divided by 2. So this will be a nice handy way to get that side length that we want to pass into our get square area function. And I like to break all my stuff out into separate methods where I can. Really make them all small and focused and easy to understand. So, to set that up, let's say double small square side equals and then for this one we knew the hypotenuse length was again the diameter, right? Diameter. If you recall, remember looking across this way. It's the diameter of the circle. So, yeah, that'll make that easy. Give us back a side. We pass this as an n. I'll make it double to keep it the same. And we'll mark this as a floating point. You probably don't have to do that. I think by declaring it a double, it'll do the right thing. I'll just leave it like this for now. Let's see where we at. So we've got the small square side. Now we can get the area using our helper function for that. So I could say double small square area equals small square side. Okay. And then for the difference now, we've made that quite easy. We can say return large square area minus small square area. And yeah, it becomes relatively simple and short when you kind of make these helper methods. So, one thing to note though is that they want us to return the result as an integer. So I'm going to round the result of this. I don't recall if we've used math round, but you can see it here. Round a double to the nearest integral value. So that will do what we want. Turns. It does return double instead of an integral type. So we'll get the round and then we'll convert it to an integer. That'll probably be the best way, because if we don't do the round, then it might take a high decimal and just truncate it. And I don't know with their unit tests if our result will come out right if we don't. But you know, that could be worth testing. So maybe we'll just leave it like this and see. That could be a good test. But I think we should probably round and then convert to an integer. So if we got everything there, double diameter, square area, math round's going to return a double. I'm going to call it as an integer. Let's just round it and take the integer. If you want, you can try removing the round and simply casting this result to an integer. Here, we'll do what we said. We'll say we'll test it without rounding and see if it comes out okay. So good. This is kind of telling, right? Look at this. It started off good. Oh, but wait. Expected 50, but was 49. So it's, that kind of gives you an indication we did the right thing here, and we're off by just a hair, right? And so, yeah, that kind of leans back toward what I said about rounding the value. By simply converting to an integer, we could have truncated a situation where the number should have been rounded up, where it was greater than 0.5. You should round that up. And that's probably what they were expecting in their test results. So let's add that math round back in. See if that fixes everything. And sure enough, it did. That final test there came out right. So good. Couple notes. Some of these things I didn't have to, like I could have taken this as an integer, the hypotenuse length, because it was derived from the diameter, which was simply doubling an integer value. If you double an integer value, it's going to be another integer. I just made a design decision here to just say, hey, I'm going to work with doubles from the start and then only go back to integer at the very end. And you may have tried doing this with even your area calculations, which you may have thought at first would be okay to use integers, but then you'd run into trouble getting these sides, which don't come out necessarily to integers, and then you start getting a lot of truncation early, and it skews all your subsequent calculations. So yeah, I like to stay as precise as I can from the start and then do my conversion at the very end to sort of get the most precision out of the process. So yeah, don't beat yourself up if you were running into trouble there where you were, close with your results but just a little off. But otherwise, I think we're good. Yeah. If there are any questions, be sure to hit me up. Otherwise, I'll see you in the next challenge. Thanks for watching.